Greetings and namaskar to each one who came here to watch this video.
Topic of today's video is potential functions, that is scalar and vector potentials. Well, we know that these are the four Maxwell equations. Del dot E is equals to rho upon epsilon naught, which is Gauss law. Second one is del dot B is equals to 0, which is Gauss law for magnetostatics. The third one is del cross E, that is equals to minus curly B upon curly T, which is Faraday's law. Fourth one is del cross H is equals to J plus curly D upon curly T, which is Ampere's modified law. So these were Maxwell's equations. Now moving to the main topic, that is scalar and vector potential. So we already know that we represent scalar potential by phi and vector potential by A. Scalar potential is in electrostatics and the vector potential is in magnetostatics. Since in electrostatics, that is del cross E is equals to 0. So from here the E, that is electric field, we can write this E as the gradient of the scalar potential and we will write it in terms of E. So we get E as the gradient of a scalar potential, that is E is equals to minus del phi. Now talking about magnetostatics, we have B, which is magnetic flux density. So we will write B in terms of vector potential as B is equals to del cross A. Now let's use this value in Faraday's law, which is Maxwell's third equation. Del cross E is equals to minus curly B by curly T. Now putting this value of B into Faraday's law and doing simple mathematics, we can solve it as placing the value of B here, and we can rewrite it as taking del outside minus del curly A upon curly T. Now taking this term left hand side, we'll get this equation. And now let's take del common from these two values. So we can write it as del cross bracket E plus curly A upon curly T. And now let's add a value which will not impact this equation, that is adding del cross del phi. This is equals to 0. So this will make no change in this equation. We can use it. Now taking this value to the right hand side like this. Now cancelling both del from each side, we will finally get E plus curly A upon curly T is equals to minus del phi. From here we can get the value of electric field E by taking this curly A by curly T to the right hand side, and finally we get this equation, that is E is equals to minus del phi minus curly A upon curly T. So here in this equation you can see both variables, that is phi and A. Phi is the scalar potential and A is the vector potential. This means that the quantity with vanishing curl can be written as the gradient of scalar potential phi, like this. Now you can see from this equation, the electric field is composed of two parts, that is minus del phi and minus curly A upon curly T. So the first part, it is due to the charge density rho, and this second part is due to the time varying current J. And we know the values of the scalar and the vector potential phi and A, that is phi equals to 1 upon 4 pi epsilon integration V dash rho upon R dV dash, and vector potential, that is A vector, is equals to mu upon 4 pi integration V dash J upon R dV dash. These are the solution of the Poisson's equation for electrostatics and magnetostatics. These solutions may themselves be time dependent because rho and J may be functions of time, but they neglect the time retardation effect associated with finite velocity of propagation of time varying electromagnetic fields.